Welcome to Module 22 of the Six Sigma Institute's Lean Six Sigma Certification Curriculum, which follows both the Council for Six Sigma Certification and the International Association for Six Sigma Certification Bodies of Knowledge. A full copy of the Council for Six Sigma Certification's Book of Knowledge can be downloaded from the course description section for free. In this module, we will be discussing sample size and its calculation. This module will take approximately 50 minutes to complete. At the end of the module, there will be a 5-question quiz on the topics discussed, which you can complete on your own at any time. You will also find several Six Sigma tools that you can download, including a sample size calculator, which is an Excel file. Accuracy in inferential statistics requires that you have the right sample size. Six Sigma teams should never make decisions based on statistical analysis when the sample size is not big enough to create an acceptable margin of error. Teams take samples because they want to determine information about a population. It can be very difficult, expensive, or impossible to run statistical calculations on the entire population. However, when we have a sample of the population and draw inferences from those samples, there is always some form of risk. The uncertainty associated with sampling is defined by the confidence level, which is also called the margin of error in some applications. You have likely read or seen survey or poll results that reported with a margin of error. The fans are 93% in favor of the new team colors, plus or minus 2%. The margin of error in that particular survey was 2% or 0.02. We can make our hypothesis test more accurate by defining power and sample size for our data, particularly when we are pulling the data ourselves and can choose how many samples to take. Minitab is a statistics package developed at the Pennsylvania State University in 1972. The statistical analysis program automates the calculation and creation of graphs, allowing the user to focus more on the analysis of data and the interpretation of the results. Today, Minitab is owned and distributed by Minitab LLC, and a single named user subscription starts at $1,610 per year, but can cost more than $3,100 per year with add-ons. They do offer a 30-day free trial of the software for those who want to take a closer look at it. When we previously discussed the different types of discrete, continuous, normal, and non-normal distributions, each of the distributions we showcased were created using Minitab. We will also be touching on how to use the program as we continue this Six Sigma training. Hypothesis testing results in either a pass or fail, where you can either accept the null or reject it. Therefore, there are two possible errors resulting from choosing incorrectly. In this section, we are going to take a closer look at the two possible testing errors that we may face in a Six Sigma initiative. We need to review these errors when talking about sample size because choosing the correct sample size effectively reduces the risks associated with each of the testing errors. The greater the sample size, the lower the risk. The risk continues to drop as the sample size increases to the point where the sample becomes the entire population of data. A type 1 error occurs when you reject the null hypothesis during a hypothesis test, when in fact the null hypothesis is true. You might reject the null that the mean of the sample is statistically the same as the hypothesized sample, deciding instead that the sample mean is statistically greater than the hypothesized mean. If the sample mean is, in fact, statistically the same as the hypothesized mean, you have a type 1 error. Type 1 error risks are denoted by alpha. As we discussed previously, the type 1 error is also called the producer risk. In a manufacturing environment, if the null hypothesis is true, but it is rejected due to a type 1 error, then material that is within specification Material that is statistically the same as the target will be rejected. This is a producer risk. It causes waste, extra costs, and lowers employee morale. A type 2 error occurs when you accept the null hypothesis when it is in fact not true. If you accept the hypothesis that the sample mean is statistically the same as the hypothesized mean, when in fact the sample mean is statistically greater than the hypothesized mean, then you have a type 2 error. Type 2 error risks are denoted by beta. As we discussed previously, the type 2 error is also called the consumer risk. In a manufacturing environment, if the null hypothesis was false, but is accepted anyway due to a type 2 error, then material that is not within specification, material that is not statistically the same as the target, is accepted. That means that a product does not meet the target and is passed on to the customer. That is a consumer risk. It causes returns, unsatisfied customers, poor brand reputation. The appropriate sample size can reduce the risk of either type of error. In order to calculate the sample size, we need the alpha, beta, and delta levels. The standard deviation, the type of data, and the type of test we will be conducting. In this section, we will be discussing the information that is needed in order to choose the correct sample size. We will be going over the alpha, beta, and delta levels, the guidelines to follow when setting these numbers, and how the calculation of sample size is different depending on what is being tested. Because the outcome of your hypothesis tests are going to be used to make real-world decisions, you have to truly understand what the test and its outcome mean for the business, employee, and consumer. That real-world understanding helps you to set appropriate alpha and beta values. The alpha level you have to set. Remember, the default in Minitab is typically set at 0.05 or 5%. When selecting the alpha level, we need to ask, what are the costs associated with an unnecessary change if the team makes a mistake in rejecting the null hypothesis? The beta level can be set by the experimenter and a sample size calculated from that number. If the sample size is fixed, then the experimenter usually sets alpha and calculates the beta risk from the sample size. When selecting a beta value, we need to ask, what is the potential damage or cost if defective materials are passed on to the customer? The delta level is the practical difference the experimenter wants to detect using the test. When selecting a value for delta, we need to ask how small the difference has to be before it becomes practically insignificant to the customer. The delta value, or critical difference, should always be based on business needs. Do we want a half sigma improvement or a 2 sigma improvement to the process? While values for various factors in sample size calculations should be guided by the business needs and purposes of the test, there are some guidelines that Six Sigma teams can follow for baseline values or if no other information or needs are present. We usually set the alpha risk at 5% or 0.05. In most instances, you can choose a beta risk between 10% and 20%, which will give you a power of 90% to 80%. A power of 90% is less likely to produce a type 2 error than a power of 80%. But it will also require a much larger sample size in most cases. And the delta value are absolute values, which will be required by business needs as a function of standard deviation. Just as there were numerous hypothesis tests to cover a range of data types and questions, there are numerous sample size calculations as well, all of which can be performed in Minitab. In this section, we will discuss the different types of sample size calculations that are available in Minitab and what circumstances we would use each of them in a Six Sigma initiative. We will talk about the differences between testing means, variance, and proportions. We will also show you the sample size power curve that will be created by Minitab for each calculation. In order to determine the sample size for the one sample t-test, we could manually calculate this value or simply use Minitab to calculate it for us. If you choose to go the manual route, then the sample size is equal to the sample mean minus the proposed constant for the population mean, which is divided by the sample standard deviation divided by the square root of the sample size. The one sample t-test for testing means and is used to compare the sample against a target value. In order to conduct this test, you should already have sample statistics about the population. In order to determine the sample size for the one sample z-test, once again, we could manually calculate this value or simply use Minitab to calculate it for us. If you choose to go the manual route, then the sample size is equal to the sample mean minus the proposed constant for the population mean, which is divided by the standard deviation of the population divided by the square root of the sample size. The major difference between the t and z-test calculation is the standard deviation. The one sample z-test is for testing means and is used to compare the sample against a target value. In order to conduct this test, you should not already have sample statistics about the population. You do not know the standard deviation. To determine the sample size for the two-sample t-test, we could manually calculate this value, or once again just use Minitab to calculate it for us. As always, if you choose to go with the manual route, then the sample size is equal to the mean of sample 1 minus the mean of sample 2, which is divided by the square root of s squared multiplied by 1 divided by the sample size 1 plus 1 divided by sample size 2. S squared is the sum of the value of each variable in the sample 1 minus the mean for sample 1 squared plus the 2 sigma sum of the value of each variable in sample 2 minus the mean for sample 2 squared, which is divided by the number of variables in sample 1 plus the number of variables in sample 2 minus 2. The two-sample t-test is for testing means and is used to compare the means from two sets of data. With each test that we have covered so far, the calculation for the sample size has become more and more complicated. In order to determine the sample size for the two-sample variance test, it is best if this is done using Minitab, as it is a very complicated formula compared to the t and z test. The two-sample variance test is for testing variance and is used to compare the variance between the two sets of samples. As was with the two-sample variance test, the one-sample variance test formula is also extremely complicated. Therefore, it is best not covering the manual calculation here and just suggest that you use Minitab or another statistical software program. The one-sample variance test is for testing variance, and it is used to compare the variance from a single dataset against a target. In order to determine the sample size for the one-sample proportion test, as was the case with the previous test, it is best that this is done using Minitab or any one of the many other statistical analysis software that's available out there today, as it uses a very complicated formula compared to the t and z tests. The one sample proportion test is for testing proportions, the rate of x per y, and is used to compare the rate of one dataset against a target. As with the one sample proportion test, the two sample proportion test is extremely complicated. Therefore, it's best that we use Minitab or another statistical software program in order to calculate it. The two sample proportion test is for testing proportions, the rate of x per y, and is used to compare the rate from two sets of data. Because we are dealing with more than two sets of data, the analysis of variance or ANOVA sample size calculation can be quite complex and tedious to do manually. There are several software programs, including Minitab, that can calculate the sample size for conducting an ANOVA hypothesis. The analysis of variance is for testing means and is used only when there is one factor for x, but more than two sets of data. The most difficult sample size calculation is that of the design of experiments. Because we are dealing with more than two sets of data and different factors for x, the design of experiments sample size calculation is the most convoluted. Like with the ANOVA test, there are several software programs, including Minitab, that can calculate the sample size for conducting a design of experiments hypothesis. The DOE is for testing means and is used when there is more than one factor for x and more than two sets of data. In order to understand more about running and analyzing sample size tests in Minitab, we will walk through the process for most of the test types. As the software was designed to make it easier for running statistical tests, its use is fairly straightforward. And other than individual options for each sample size calculation, all of them are conducted in the same manner. So in this section, we are going to discuss the sample size calculation for a one sample t-test in Minitab. The same steps can then be followed for any of the other sample size calculations you may need. In order to conduct a sample size calculation, we need to select the Stat menu option from the top ribbon. Here, you will see a lot of statistical functions of the program, such as control charts, regression testing, analysis of variance testing, and even design of experiments. What we are looking for, however, is the power and sample size at the bottom of the drop-down menu. As you hover over it, a new menu will pop out and give you the option of Sample Size Estimator, which is just a general sample size calculator. The menu is then split into groups, a group for means test and a group for proportion tests, a group for variance tests, and a group for more advanced ANOVA and DOE tests. We are just conducting a one sample t-test, which is the second means test option. As soon as you select the one sample t-test option, a dialog box will pop up and give you four fields. The first field is the sample size, the second is the differences, the third is the power value, and the fourth is the standard deviation. Since we need to know the sample size, we will leave that option blank. We need to fill in at least three of the four fields in order for the calculation to work. The differences are the delta value, and this is entered as a multiple of standard deviation. The power values are your beta value. Remember, we previously discussed the beta value should be between 10 and 20%. Here, you would enter a 0.8 for beta of 20% and a 0.9 for a beta of 10%. You can actually enter them both and it will output both options. Lastly, we need to enter in the standard deviation of the data. We discussed the calculation of the standard deviation previously. Before clicking OK, you will want to check the options. Once you click on the options, another dialog box will pop up. Here, you will be able to adjust the hypothesis. Remember, the null hypothesis is that there is no change in the status quo, but the alternative hypothesis is that there is a change. Here, you can choose the change that you want to set, whether it is not equal to, less than, or more than. For sample size calculations, we want this set at greater than, and then we can adjust the confidence level if needed. It defaults to 5%, but you can adjust the alpha level depending on the business requirements for the risk. Once you click on OK, the options dialog box will close, and you can go ahead and click on OK again to close the sample size calculation dialog box and start the calculations. A summary will be printed out on the workspace and will provide the test name. It will state that, in this case, you are testing the mean and that your hypothesis is the null versus greater than the null. Because we selected multiple differences, multiple deltas between 0.5 and 2.0, and because we selected two power values, 0.8 and 0.9, the printout includes the sample size for each possible combination of power and delta. Now the team will have to decide which sample size is best for their needs. Is it within budget and scope to randomly select 168 samples? Or are you limited to a maximum of 50 samples? Always remember that the greater the sample size, the more accurate your conclusions about the population will be. Before moving on from sample size calculations, it is worth noting again the importance of random sampling. Even if you perform a calculation to determine an appropriate sample size, and you choose to err on the side of caution by sampling at the largest count size returned by Minitab, you can still draw the wrong inferences because the sample was not random. Dogbert illustrates the exact opposite of what we want from a random sampling. Here, he is being paid to show that the product is safe and nothing else. So he called one person, who was obviously alive since they were able to answer the phone, and asked them if they have ever been killed by a poorly designed product. He clearly biased the sample because he was choosing the wrong method of data collection. In Six Sigma, we never want to be like Dogbert.